Hello everyone. We all know that the modern theory of physics, painstakingly constructed by scientists over the years, remains incomplete to this day. Despite efforts to search for a deeper theory, all attempts have been disappointing. Everything we know is encapsulated within the Standard Model, which suggests that the universe is made up of matter and antimatter. When these two types of matter collide, they annihilate each other to create energy. For example, when an electron collides with a positron, typically this combination produces a pair of gamma rays. In some other cases, at higher energy levels, it may produce particles like Z, WB, or mesons. According to the theory of symmetry, after the moment of the universe's birth, matter and antimatter would have completely annihilated each other, leaving behind an empty and meaningless universe. However, somehow ordinary matter still persists, eventually forming galaxies, stars, planets, and life. This anomaly, known as Baryon asymmetry, remains one of the greatest mysteries of physics. Scientists have proposed various hypotheses to explain this asymmetry, but the truth is we don't know which, if any, are correct. One of the most plausible hypotheses is that after being created, matter underwent self-decay to produce even more matter. This gradual process disrupted the balance, resulting in the universe we observe today, composed mainly of ordinary matter. While the decay of particles may not be the sole cause, it indicates that the theory of supersymmetry is imperfect and requires re-evaluation. This poses a significant question. Was the universe symmetric or asymmetric after its birth? If it was symmetric, then every particle we know in the Standard Model would have its own antiparticle. Conversely, there are many other types of supersymmetric theories that help describe everything in nature. On the flip side, partial or complete asymmetry could be hiding many new particles and physical phenomena, because all particles in the current Standard Model have their own antiparticles. So, if ordinary matter decayed into more particles than antimatter, there must be some undiscovered particles in nature. Before delving into deeper issues, we need to understand why scientists believe that the universe was born with both matter and antimatter. How do they know this when the universe today is primarily composed of ordinary matter? This is not mere speculation. When matter and antimatter combine, they produce high-energy photons, and clues about what happened are evident in the cosmic microwave background radiation, the oldest light in the universe that we observe today. According to this, the ratio of ordinary matter particles to microwave background radiation photons is about 1 in 10 billion. This indicates that at the moment of the universe's birth, the quantity of matter and antimatter differed by an extremely small amount. For every 10 billion antimatter particles created, there was one extra ordinary matter particle that survived, eventually forming what we see today. Essentially, this is an incredibly small asymmetry, but its consequences are profound. Today, we live in an energetically charged universe, with ordinary matter making up about 5% of its total mass. Scientists are still trying to understand why the universe exhibits such asymmetry. While it is only a very small asymmetry, it remains a massive mystery. So, how do scientists decipher this problem, and have they solved it yet? Overall, this is undoubtedly a difficult issue because it is not without reason that it is called one of the greatest mysteries of physics. Over the past few decades, scientists have been trying to find what is known as the electric dipole moment of the electron, one of the most challenging and time-consuming searches in the history of science. So, what is the electric dipole moment of the electron, and what does it mean? Essentially, the electron is a tiny particle, but it does not exist alone. Surrounding the electron is a cloud of virtual particles, much like how the electron surrounds the atomic nucleus. These virtual particles act around the electron like the magnetic field of magnets. In terms of quantum mechanics, This is called the electron's quantum field. Every particle has such a field, and they interact with each other. If there are unfamiliar particles corresponding to unfamiliar fields, they may affect the electron cloud, making it asymmetrical. In other words, this interaction causes the electric dipole moment, which is expressed by the difference between the center of mass and the center of charge. This difference has never been detected, and it is probably much smaller than what experiments can measure. If this is true, scientists will have to add new types of particles to the standard model to explain the imbalance of matter and antimatter. Now, let's connect this with the theory of supersymmetry. If nothing happens, the electron will exist as a spherical blob. Conversely, the electron will be slightly elongated, meaning its electric dipole moment is not zero. The task of scientists is to determine whether electrons are round or elongated. The actual nature of this is to measure the difference in the center of mass and center of charge. To discuss this experiment in detail would take a lot of time, so I'll briefly explain it for everyone to understand. For an experiment on electrons, researchers will select atoms for study and a vacuum chamber to isolate them from other atoms. The atom chosen for this experiment is hafnium fluoride because it is one of the heaviest metals on the periodic table and does not have radioactive properties. But there's a problem. How do you keep the experimental atom from colliding with the chamber walls? The answer is to let it levitate. Researchers will ionize the atom to create electrical polarity and generate two magnetic fields at the ends of the chamber. When the atoms are charged, they will easily be attracted by the magnetic field, flying from one end of the chamber to the other. With the experimental chamber designed as a long tube, the observation area is usually about 1 meter long. The weakness of this method is the rapid movement of atoms, which can reach hundreds of meters per second. So, the actual observation time is only about a millisecond. This led to a lot of data being missed, which was recorded without purpose and not saved. To overcome this weakness, scientists reversed the magnetic fields at both ends of the experimental chamber at a sufficiently fast speed. The atoms, instead of flying in one direction, would be pulled back and forth in the middle, and this method is called a magnetic trap. If the experimental chamber is made into a circular shape, the atoms inside will move around. This creative idea extends the observation time from 1 millisecond to 3 seconds, a breakthrough change. The measurement time for collecting such data is about 2 months, with a total of over 100 million electrons recorded. Then scientists spent more than 2 years calculating errors. After many years of work, the final result of the experiments is zero. No electric dipole moment of the electron has been observed, at least not in this case. Due to concerns about unwanted errors that could affect the results, scientists are planning a more modern, elaborate experiment lasting about 10 years. However, up to the present moment, the electric dipole moment of the electron is still zero. And this is a result that speaks volumes. The electrons themselves are still perfectly round. The theory of supersymmetry has not been overturned, and the mystery of antimatter remains. If you have any antimatter particle and throw it into the Milky Way, that particle will exist for a maximum of about 300 years before it combines with a particle of the same type and annihilates itself. This shows that the amount of antimatter compared to ordinary matter in our galaxy is 1/8 in 10 to the power of 15. Furthermore, observations spanning from hundreds of millions of years to 3 billion years of light also show that the amount of antimatter currently existing in the universe is virtually zero. Because if there were any, they would interact with ordinary matter and create gamma rays or X-rays that could be observed from Earth. Today, scientists can be certain that the current universe we observe is composed of 99.999999% ordinary matter, and the reason for this asymmetry remains a mystery to this day.